Okay, welcome back. Uh, so now I would start inviting the speakers come and talk to us. I will just go in random order since usually we start 4 to 1. I will start with 2. So room number 2, seeds and dynamics. Sorry.
Hi everyone, I'm the speaker for room 2, and the topic of our discussion is seed and dynamics, whether we can do one without the other. And so in the first minute of the discussion, we decided that the answer is no. So is there room to discuss more? We still discuss for like 1 hour, so there's a lot of things going on there. So the reason why we cannot only include one without the other, especially we cannot model seeding without considering the dynamics, is that if you consider dynamics, then the picture that you get will be very different because, for example, as Leclerc mentioned today, like in his model, the seed will merge pretty efficiently. And that's one of the assumptions that allows us to produce these overmassive black holes, even with relatively light seeds. But then there are a lot of, and people like in the discussion bring about a lot of mechanisms, especially at high redshift, which will stop the seed from merging and growing efficiently. So that includes, for example, the highly irregular shape of the high redshift galaxies, the clumpiness of the high redshift galaxies, which will scatter around the black hole. And also if there's no well-defined potential well for the black hole to sink, then it's very hard to merge the black holes. And this is especially hard if the black holes are bare, meaning that if they are not embedded in stellar clusters. So some people think, oh, that might kind of should we rule out like POP3 star formation, especially like rule out the possibility that these are the main mechanism for producing the massive, very massive black holes at high redshift. So that's some speculations that people have. And what else did we discuss? And so there are also questions on, for example, if we consider both seeding and dynamics, and if seeds don't merge so efficiently, where are we supposed to find them? And people suggest that there have been works showing that they should be wandering on scales of roughly kpc, and depending on how efficient they merge, we might expect a lot of wandering black holes, but we don't found a lot of them so far. So where are they? Like, why do we not see enough of them? That's also a question. And finally, so since we say, oh, we should combine both mechanisms, so far it seems that not a lot of people have been doing it. And the reason is, as Leclerc mentioned, that it's maybe better to understand like these things separately before the two fields can start talking to each other. But eventually it will be very important that, for example, the people who work on the seeds can inform the dynamics people, like where are the seeds formed and how many of them form, so that the dynamicists will be able to model these in the dynamics and see how many of them can manage to sink efficiently to the center and grow and so on. I think I've covered everything. Marta is also in the discussion, so in case I miss anything, you can say more.
I didn't even remember when I called number 2, I forgot that it was ours. Comments, questions?
So with the effective dynamics on growth, um, what what are the key processes that we're worried about? Is it like dynamical friction, black hole recoil? You know, is there maybe a small number of these such that you could, the way that we've been talking about, like, um, you know, linking multi-scale simulations of like galaxy evolution, could we similarly have like a library of high resolution black hole dynamics models, right, that could then be used as a prescription for coarser simulations as an effective seed model? Does that make sense? Like, instead of saying, so let's say you're a lower resolution galaxy evolution or cosmological simulation with maybe not a good model for dynamical friction, could you still have an effective model for a black hole seed that is actually informed by physically reasonable simulations of black holes with realistic dynamics?
Yeah, I think that's a very good idea. And I think that's like the direction that maybe we should head to. And in terms of the effect model for dynamics, like I mean, it is depending on like how complex you want to build the model. Like for the first order, we can have this dynamical friction formalism, like Chandra sector type. But one problem that I see and people in our discussion group brings about is at high redshift, because the galaxies are so irregular, like the dynamics can be very chaotic. And I think probably like we can build a more statistic model for like the distribution of the seas as a function of like radius or mass or something. I think that is possible, but I'm happy to hear other people's opinions.
Comments on these or new questions?
New question, but so it's kind of one, I guess, for the audience. Like, if we want to put in the dynamics of the light seeds, I'm thinking more into the hydro simulations. We do need to worry about the numerics for that, though, right? So obviously, like, you know, Michael Tremmel and Hugo have put in subgrid modeling of the dynamical friction into different codes. But my understanding of that is that it'll still only work as long as the dark matter mass is comparable to the seed mass. Okay, I think you basically need to have them the same. From talking to Michael.
The black hole has to be 3 to 10 times the mass of the
larger. Yeah. Okay. Yeah. I think he was kind of telling me, you know, be okay nearly if they're the same, but like, okay, yeah, fair enough. Yeah. It certainly can't be less. Okay, so that still puts a fairly strong constraint on like what you can do in your simulation. You know, that's going to be a problem, because if our seeds are 100 solar masses, then our dark matter resolution needs to be 100 solar masses. Like, if you do the numbers on that, the box size is pretty small pretty quickly. So I don't know if people have comments on that, maybe who've implemented these schemes.
Something went wrong. Please try again.
Yes.
That's very good.
Yeah.
So something we do for dark matter is to smooth the dark matter potential. So we can, in Ramses, we can tolerate a higher dark matter mass, but then we are still limited by the stellar mass.
Yeah.
Stellar particle mass. So I don't think that we can get a way out, but.
If you smooth the dark matter, this is true, but won't you take away the dynamical friction component of that then?
No, well, you will just have a smooth potential instead
Yeah.
of a granular
It
one.
won't be noisy, this is true. Yeah.
But you have the force.
Yes, but it's smooth.
But dark matter,
Yeah.
I mean, I think that the stars are so messy that you cannot tolerate ignorance on dark matter. My feeling, but I may be wrong.
Yes.
In this respect, well, I'll talk about it tomorrow, but yes, I think we could do something about that with dedicated simulations with very high resolution. If we can sample a bit what happens in the early phase and see if that maybe if we resolve the dynamics better, this black hole might grow a bit. Then we might use these to devise some subgrid models for large scale simulation. But first, we need to do this step, and it's quite demanding.
More questions or comments? Yes.
This might sound like a crazy question, but just like how we do super Lagrangian refinement for gas around the vicinity of the black holes, can we do something similar for the dark matter around the vicinity? Resolve dynamical friction locally?
So you mean, can I like re-ask? So you mean hyper refine the dark matter?
Yeah, basically
around the
create
black
smaller
hole?
dark matter particles from the larger particles.
And star particles.
And star particles.
Yeah.
I know the question is how do we distribute them, but maybe.
Yeah, that's right. So I think
Sorry for putting you on the spot.
I think yeah, the issue with collisionless particles is I guess the phase space distribution of the way you split. If you start splitting like dark matter particles, the same for the stars, then you have to define their position and their velocities, and then the phase space distribution of collisionless particles will not just die away. So the good thing about the gas is you introduce perturbations when you split the gas particles, but they're like mini shocks and things, and very quickly things stabilize. So the new equilibrium resolution in phase space for like stars or dark matter, collisionless particles, that doesn't go away. So yeah, I'm not sure whether that's. I heard some people saying never touch the phase space because it will be totally wrong, and then some of the people say the impact will be like minimal compared to like how much we don't know about feedback. I heard the two extremes. So yeah, I don't know. So that's yeah.
Well, yeah, kind of just following on from that, I guess if you have particles of different mass, collisions particles of different masses as well near to each other, then you get spurious n-body heating and things being ejected, and yeah, unfortunately not, I don't think.
I mean, you could do something similar to how they do zoom simulations, create a gradient of.
That's true. You're probably better off just running a zoom simulation, I guess.
So it'll be a zoom business.
Anything else on this? Not, let's thank Yanni again. Now we choose room number 1.
So the title was Small Scale versus Large Scale. What physical models of massive black hole formation should we use in 2024 plus, so in the next years? So I guess we spent the first bit kind of highlighting what are the caveats of current models. So having this kind of fixed halo mass or fixed gas mass, and how that is not really realistically anymore. Well, probably it has never been realistic, but I mean, it's becoming somehow outdated. And so then what can we do for the future, right? So for sure, the direction in which we went was to suggest or to envision models that become more and more complex to capture the actual intrinsic complexity of seeding processes. And well, that's not an easy thing to do. So we kind of also thought how this could be actually implemented in reality instead of only dreaming about it. And well, I guess one of the main take-home messages for what we discussed about is that different models should start to talk to each other, and especially the interplay between semi-analytical models and hydro simulation up to this year has not been probably the greatest ever. So this is surely something we can work on as a community and inform each other. So use hydro to have better subgrids for sums and then test these subgrids with sums in order to tell hydros whether they are doing things good or not. And yeah, another cool thing that I think is worth mentioning is that we thought it could be useful to have probably one hydro sim and then plug in different seeding models so that apart from the seeding model, the rest of the context in the simulation is the same. And so this would be a very cool way to actually compare the outcomes of seeding models between each other. And that's, I think, all of it. If you from the room will want to add something, feel free.
Not, you can ask questions or make comments.
Very clear.
So basically, we would take like the Renaissance simulation, and we will all like kind of try to see where we would put the seeds with our own models. That's the idea. That
Yeah. One of them was that, or also somehow I think like really try to see if this approach of having fixed threshold is something that is worth keeping on, or once you kind of implement more and more complex physics inside, it does make sense to keep this somehow now outdated approach, or if different things like interact with each other, I guess.
Yeah, I think we were kind of throwing out that idea as just something for maybe people to work on. But yeah, the other thing I think we also touched on in the discussion was maybe the lack, this binary light seed, heavy seed model that had been there in the past. Perhaps maybe we change that to be more of a continuum, so that we don't just go from everything at 100 solar masses plus everything at 100,000 to being a continuum between the two. And I think that would be something that could be implemented in the SAMs as well, and would be very informative.
Yeah.
you put like a distribution for each model. Or do you have like a continuum? I guess you just like that collapse.
That's a really good question. I don't know. Like, when you the answer to that, I wouldn't be here. But no, I in the sense, a continuum, like I just mean that there will be more 100 solar mass seeds than there will 100,000 solar mass seeds. So yeah, and then you have some sort of a distribution that goes from one to the other. The shape of that distribution, I don't know, of course. But we could at least try and see how that impacts. And the other thing is, because again, it's quite binary at the moment. I think it's binary because we didn't really know what to do before. I don't think we know any better now, but I think it at least works. I think that will be an improvement. And then on the light seeds, it kind of feeds back into the dynamics conversation. Perhaps random walks within those smaller galaxies for the light seeds would be no harm as well. I think that would probably be. I think Rachel, I'll hand over to Rachel a bit here, but Rachel had a good idea on the sloshing approach for that.
Perhaps. Like a duty cycle where
yeah.
in some time scale for some period for sloshing and only let it accrete, when it's like sitting in
exactly. Yeah, which would be ideal.
Which you could then calibrate with
a hydro.
The hydro.
Yeah. So like I think the other thing, and Danielle has already mentioned this, is to have like hydro-informed semi-analytic models where we kind of talk back and forth to one another and one improves the other.
I just want to add one thing here, that we should not forget physics in any case. So the distributions should be physically informed in some sense in terms of the numbers and the typical masses, because I mean, this whole game started exactly with this. What are the initial conditions? I mean, should they be just random numbers, or do we want physics behind it? So, I mean,
it's hard to put the physics behind these.
No, but I mean, that's what you guys are doing, right? With the Renaissance simulation with.
Yeah. Oh, yeah. Okay.
I mean,
yeah.
It's physics. It's not just magic.
Yeah, sure.
Yeah.
Okay. It was definitely magic with the 100 and the 100,000. Like, there was an element of magic there. And I'm just saying, yeah, you're right. It's more of a learning, but I wouldn't say we've I still don't know the shape of that distribution.
No, but I think that it should be physically informed. So
Yeah.
just not take, yeah, we took 110 to 5 just because they looked like good numbers. Honestly, if I had now to justify them, I would say that they were just good numbers. So like the 10% relative efficiency, it's the same thing.
Yeah, yeah. Yes.
More on this. You had the hand up? Something on this side? So are we all, we all know what to do next year, 2024, which is coming in a few weeks when we put black holes in our models. Yes. Okay, looking forward to read the papers. Okay, let's move to room number 1. No, number 3, because this was 1, right? Yeah. Number 3, which was the growth of seeds and JWST. Do they need special treatment? And any random 2.
I can use this one.
Right. So we spent quite some time talking about observations, a room of theorists, with talking about observations, and specifically, I mean, you may guess it. Do we trust the observations? So the thing is, yeah. So one example is, we already have trouble with the measurements of stellar mass around the local universe and close to redshift 2, and how reliable are we with redshift 7 and above, and the SED modeling and the star formation histories, the black hole measurements, like Jenny also mentioned, the luminosities. And we also talked about supernova feedback, how that could play a role in low mass galaxies, high redshift, and in the accretion history of black holes. One thing was to, I guess, probe the X-ray detections. Can we do better with X-ray detections of black holes? And does anyone have any idea of radio observations at really high redshift, also meaning like redshift 6 or so, that we just didn't know about? We also spent a lot of time talking about these overmassive black holes and how can we try to explain them. And then we went back into reliable masses, reliable black hole masses, stellar masses. So yeah, I guess the consensus after that was, can we better understand them at redshift 3, and can we have other physically motivated things that could happen, such as stripping of a black hole and of the black hole's galaxy, and maybe have this black hole be massive in a less massive galaxy, or some other evolutionary event of mergers and so on. So,
well, yeah, the other thing we think about kind of the overmassive black holes was from a recent result from Roberto Maulino's group of finding that if you compare the black hole masses to the velocity dispersions or the inverted dynamical masses, they seem to match the nice trends that we have from redshift 0, but the stellar masses don't. So is this a stellar mass modeling problem, or is there something else going on with feedback here that we're not sure of that's stopping this these stars from forming to some degree, or something else entirely, I guess, was the other thing we were looking at. And yes, eventually we thought, okay, we can't just keep bashing observations. Let's say these are realistic, right? Now what do we do? And so then we started talking about the seeds, and there's been some interesting talks earlier today from John, among others, about saying that the most massive seeds that we seem to be able to form in these high high resolution, high redshift simulations are A, 10 to the 4 at most, and B, not in the centers of galaxies. And but yet to various models to try and grow high redshift quasars, you need at least 10 to the 5 plunked right in the center of a galaxy. And can those match up at all? Or do we have to rely on these kind of direct collapse black holes forming further out, somehow making it to the center in a reasonable timescale to then accrete, probably at Super Eddington by that point, to have any chance of getting anywhere near the inferred black hole masses at least. And there's kind of a lot of steps in there that we don't properly understand, that we gloss over in most cosmological models by just chucking things in the center. And that really does help us grow these things, which is not necessarily accurate for where these things should be as we go along. And yeah, the timescale argument is the big problem there. The other thing we talked about was kind of redshift evolution. And for example, we're thinking about the most massive black holes that exist at a given time. And we can see these high redshift quasars with 10 to the 10 up to 10 to the 10 solar mass black holes. A lot of the low redshift things records we see are 10 to the 10 solar black holes. But potentially in the centers of galaxy clusters, we had an interesting chat with Julie. Potentially you can infer black hole masses of a few times 10 to the 10, potentially even pushing towards 10 to the 11 solar masses. Now, and these, I think, are right in you saying that these don't lie on the relations that we expect from other observations at low redshift anyway. So are we looking at just the progenitors of clusters, BCGs, that just are weird throughout the entire universe's history? Or do they somehow fall onto the line somewhere? Do they keep their large black holes and just grow stars without growing the black hole that much more? That seems tricky because it's the same fuel source, right? And the last thing you was kind of mentioned was kind of a gap, is that we're now starting to have estimate measurements of the black hole stellar mass relation at redshift 6, 7-ish. And we have this estimate at redshift 0, but kind of this intermediate redshift 2 to 3, I think will be the interesting probe in future. We're kind of talking about whether the reasons why this hasn't been done, and possibly it's just JWST is too new, maybe. But that kind of progression over time, I think, could be quite interesting and tell us something about how these things grow and how the populations change over time. Whether you can link that back to the actual seeds or not, I think that's remains to be seen yet.
Yeah, one more thing I forgot. So we also spoke about, whether we should be, I guess, like spending a lot of time in trying to understand this overmassive black holes. But the thing is, I forgot to mention this, but like I'm thinking about, we're looking at a very small patch in the universe, and we see these overmassive black holes already. So statistically speaking, are they rare? Are they the tails of the distribution? And that's something that I think is an open question.
Yeah, I think to kind of follow up on that point, we either thought the observations are wrong, in which case we don't need to reproduce them, or they're right, but this is the tip of the iceberg, very rare. Do we change and bend all of the models to fit these kind of extreme objects? But, open question.
Okay, so just on this, we were exactly in the same situation with the redshift 6 quasars before. We knew that those were the tip of the iceberg, and I think that many people spent a lot of time modeling them. But more questions, comments on this?
So highest redshift radio allowed quasar, 6.8. There's actually a handful of objects that are detected in the radio above redshift 6. So that's, starting to get up there. There are lots of black hole mass estimates using the same kind of broadline approach in those intermediate redshifts. Maybe people just aren't aware of them, but they've been out there for many years.
They're
So
also still like the stellar mass relations and
stellar
all that.
all
Okay.
those same things and much less uncertain than the
I
ones.
guess I haven't seen that relation plotted over time anywhere.
It is. There are papers that do that, but you know, whether you believe it or not is the question. And I guess coming to that, you know, this is something I've been thinking about a lot. I would not focus on these relations in these sort of derived parameters, which, as we've been discussing, are super uncertain. Let's focus on the observables. Let's see if our models can reproduce the observables, right? Let's try to predict the luminosities or the things that we can actually observe and, you know, at least see whether there's a tension in that space. I think there's been so much focus on, like, you know, these plots that could just have such huge uncertainties. Like you said, you spent so much time talking about that. Let's think about what can we predict that is actually directly comparable to the observations. And I think that's within reach, right?
I guess the one caveat to that I'd say is that, well, we heard earlier about how bolometric luminosity estimates have a lot of uncertainties associated with them. And from the simulations perspective is we can easily calculate a bolometric luminosity, but converting that to a luminosity in a certain band that we can observe has the same uncertainties going the other way, right?
Well, not necessarily, right? I mean, we have to model dusk, we have to model obscuration, but, you know, again, then it's physics. It's not just some random prior on your stellar mass SED fitting code where there's no physical input into it, right? So yeah, there will still be uncertainties, but at least I think it's more closely tied to the physics, which is what we can actually predict in the simulations.
What about the AGN SEDs? But what about the AGN SEDs? I seem to see such a large variety in them at redshift 0, and it feels really.
Chris showed very nice. Continue, but then I think that I will ask you to comment on these SEDs.
Yeah, I mean, I would also, I mean, I agree with you. I think making stellar mocks is maybe more straightforward. Whereas I would love to, if anybody knows how to, how to make AGN, how to make predictions for the AGN luminosity in various bands, because my baseline understanding is that they're so diverse that I wouldn't know where to begin. I mean, even aside from orientation effects and things like that, I mean, they seem to be variable. They seem to be diverse. I don't know. What do we know? Can we maybe like make a library and make a statistical statement? I don't know.
I tried to model SCDs of AGN, and I was telling this to Shane. I gave up on the physics. I just wanted this to fit the observations, and it works. It's not physical. But now there is some physics behind it. You know, Chris Dunn works, but it's the tiniest bit. The rest is not physical. So since you showed those beautiful SCDs, can you comment?
Yeah, we don't know much. You're right. I mean, even for massive AGN, you see quite the diversity of whether you just have a straight power law slope, or some of them show a soft excess in their bumps, and some of them don't. About 50 of them, 50% do, and 50% don't. And we only have a handful of candidates where we know what the shape looks like in the IMBH regime. I mean, one of them would be HLX1, which I've talked with Shane about, but it's accreting in either Eddington or super Eddington. And we know that most IMBHs are going to probably be sub Eddington. And so is it a realistic one? I don't know. So, and there's multiple models out there. So I think you mostly just kind of have to pick one and go from there. And then once you've picked a model, I mean, you can account for the variations, but I mean, there's a large amount of uncertainty in there.
Okay. Well, I mean, I think that's a challenge to, I mean, okay, so the question is, how do you map things like masses and luminosities onto SEDs. We can do a pretty good job of just collecting SEDs and then saying these are the typical SEDs, and then you can bin them. And in some ways, what's surprising is they don't evolve with mass and things like that. So the physics seems to not predict that. But I guess from an observational standpoint, that's an advantage, that some of these things you might care about more, like mass dependence and stuff, doesn't actually seem to show up in the low redshift ones as much as you'd expect. So AGN tend to be, actually, I would argue, slightly more universal than they should be. And so that might be an advantage for doing this, assuming, you know, the high redshift stuff is like the low redshift, which is still maybe a reach.
So another comment on the SEDs as well as there's lots of degeneracies in the models as well, because we're assuming that A star is 0 and it's probably not. And we're assuming some Eddington accretion rate because we don't know any better. But if you're varying black hole mass accretion rate and spin altogether, you're likely to get multiple solutions. So these are good reasons to start tracking black hole spins, because these can give us priors that we can implement on the analysis. I mean, if you look at the posteriors for any of the AGN that you try to fit with these models, like with Chris Dunn's and stuff, I mean, they're quite large. So, you know, that's just more motivation to start tracking them in simulations.
I guess I would like to add just part of the reason why the room was feeling very frustrated about this part is because, yeah, we were like thinking about that. Like we're applying like a dust extinction model at redshift 0 at like redshift 10 or 6 or 7. And so that I think that's where the uncertainty came about. And I think I will go a step further when comparing with observations and using within the simulation, try to also think about the very similar way in which stellar mass is also being compared, because, you know, you have models that take twice half mass radius and it's not the same as like 1% the viral radius mass enclosed within that, or the bounded particles of the halo and so on. That can also create some scatter there.
I think we have to move to room number 4 because we have to leave the room at.
Can I just ask one question? It was just something that Rachel brought up earlier. And for growing the seeds, like let's say we start at 10 to the 5 and they don't grow, and is it because the stellar feedback is too strong? Like obviously they don't grow because the stellar feedback is too strong, right? But is the stellar feedback too strong because of numerics, I guess was the point. And I didn't have a feel for that. I don't know, Melanie, you're going to work on that.
I mean, in cosmological simulations, most of the accretion rate's Bondy anyway, so the small black holes are harder to grow to start with. I think is part of the problem, not the whole problem. If you had a shallower dependence on the black hole mass, you could grow smaller black holes more efficiently and have a lower accretion rate for very massive black holes in theory. But
well, it's going to, like, the dynamics is going to play a role as well. If you go smaller, it's dynamics, I think.
Yeah, we don't really have dynamics.
Yeah. Yeah, but if you did.
That's a blanket statement.
Yeah. But I think it's more like, is the stellar feedback impact, you know, having a spurious impact, I guess is my question.
I guess this could also depend on how the energy is being distributed in the model, right? Like if you're just throwing out all the gas, or if you're just injecting it into your ISM or gas cloud.
But may I probably remind people of Megan's paper, in which she uses analytical approach to still find that black holes below a certain mass should not grow if you want to reproduce the luminosity function as we measure. Not supernovae, something else should still give this bimodal growth rate, at least in the observable universe.
I don't know if your microphone's on. Marta.
Oh, it's
Right?
not?
To hear you.
Or probably.
Which paper?
I think it's, there was a paper on the luminosity function and the requirement.
Yeah, okay.
Yeah, I did this as an RU student, so I don't. We were seeing this like delayed growth in the virus simulations, where early on the black holes were not able to feed efficiently because there was strong stellar feedback, suppressing the growth somehow. But then once that started settling down, there was this really rapid growth phase of surely super Eddington rates, and then it was able to get to the local scaling relation, so it could start from like lower mass black holes and get there eventually, even though it looked like it wasn't quite going to get there at higher redshifts. I don't know, is that what you?
It was mostly a statement on this being a common result.
Yeah, it's seen in a lot of simulations.
Okay, so I think that we have to go to room number 4. So thank you again.
Okay, so room number 4, we were talking about, can we really do grand simulations by pooling resources, AKA the John Reagan run, or should we do something completely different? So we spent like the first 15 minutes asking, what exactly is a John Reagan run? But what we came to is like, should we take all the models? It's one question is like, what is the best model that we should use for star formation or AGN feedback and feeding, and what types of physics? So, MHD, it's really coming down to bridging the scales, which was a topic of the discussion in the past 2 days, from the horizon scale to gigaparsec scale. And below, like say below 100 RG, we need some sort of subgrid prescription for from a GRMHD simulation. But one idea that we had to do something truly multi-scale, like instead of having like a subgrid model, what about having like imagining the subgrid model actually being a simulation embedded in a cosmological simulation? So it's kind of decoupled from the simulation, but they're talking to each other. I don't know every so often, but there needs to be some high cadence of doing that. So it's like you'd have 2 simulations going on at the same time. But we didn't really know how to go forward with that. So you can imagine taking one of Hyrin's simulations of like the spherical grid that can look at the inner, I don't know, like 100 parsecs, 10 parsecs, or kiloparsec, and that being embedded in every galaxy or around every supermassive black hole. But that's within a cosmological simulation. So each one of those only uses 1 GPU. So you can imagine if you have access to the full frontier that has 10,000 nodes, 10,000 GPUs, you could create a task of these small scale simulations that are being passed to each GPU that are then taken into a cosmological scale. So I mean, that's kind of the multi-zone method. You have to, that's the biggest problem. We can scale in the number of galaxies and the volume that we're actually simulating, but to scale in time, that is very hard, right? The time scales, that's the most difficult part. Whether you can be adaptive in time, not adaptive in time, but if these can scale in time and somehow, that's a big thing. Because they're only, I think Forrest pointed this out, that clock cycles are only so fast, right? We have like 4 gigahertz, so you can't take an infinite number of time steps. And I'll talk about that more later. How do we actually deal with these multi-scale, some solutions? I also brought up, I was the one that brought this up yesterday about subgrid model libraries. Pooling resources, not only like computational resources, but effort, right? Person time. If we had a common library with different types of models in which you could focus on the physics and not really implementation into the code, right? How does that implement into the grid or moving mesh or the particles? And you could focus on the physics in which we're actually trying to discover, and we can share that among each other, and you can use in different simulations. That could be a big benefit, but that's a lot of work. We would have to find somebody that's interested in code infrastructure to actually take on that task. Usually, like, can't assign that to a student. No, someone has to be interested in doing that. Like Grackle, for instance, like Britton Smith took that on. graciously, like unselfishly. And, it's been a huge benefit to the field, and it's much easier to actually understand or have a common interface for chemistry and cooling. You can think about the same thing for other microphysics and subgrid models. But if we had one huge simulation, then we couldn't double check ourselves in between different simulations. What if we're putting all these resources into it? What if it's wrong? Yeah, you always, sorry. Yeah, they always have bugs, but if they match most of the observed relationships, that's great. But what if it doesn't? What if it's kind of missing in one parameter? Then we'd have to run the whole thing over again and try to refine that. But if we did have that, we can use that as a training data for ML emulators to actually, because the time stepping, that's the biggest issue. But if you can take some super time step, say you can skip 1 million time steps by actually emulating the physics in the solvers with ML. And that's one way to do it, to actually, to get over this time step issue. But you always have to be careful with that, whether it's providing accurate results. Let's see, what else did we talk about? We could use, let's see, sorry, I'm reading these notes. Could take additional resources to include more physics, of course, because not everyone includes magnetic fields or cosmic rays. There are all sorts of things that we could actually include, but there's still the time stepping issue. And Forrest, he pointed out said that GPUs won't solve the problem because of this time stepping issue, right? We can't use that as more computing power as a crutch. Can I plug in? There's some things that
I don't know how to do it.
I think I'll just work.
Just work if you connect the HDMI.
Oh, that's power. Is that your computer? No. Okay. Oh, there we go. Got it. Yeah, so we're thinking about emulators, and we can always look to other fields. So this is a paper from biomedical, this is on Nature, from biomedical and biological sciences, how to actually do multi-scale modeling. They have a lot more funding than us, but how to actually, it's really interesting to see how general it is of a problem, because they're trying to model things from a cellular level all the way up to living systems, biological systems.
Share this link to
Oh,
the
it's
Slack.
It's in
It's on there. Okay, great.
so I include it here. Yep. And also putting this in context. These are great. Let me see if I can full screen. There we go. Yeah, so we can combine together ML and this multi-scale modeling, but what they do is, it's a circle, it's an iterative process, how to actually make all these scales talk together, and also multimodal, right? Both modeling and also observations. It's easier to observe things when it's in the lab and it's right there, right? But they do things from a cellular level all the way up to organisms. And we do the same thing, right? All the way from particle levels and like PIC simulations all the way to the cosmological. And I think we can really learn. This is when most of the discoveries and new ideas, we have this interdisciplinary crosstalk. But this was in the, I put this in the document here. Yeah, but so it's not any problem. Other fields are actually looking at it, like material science, they have the same problems.
Climate science.
Climate, yes, yeah.
Similar.
That's actually where I first saw ML being used, emulators.
Yeah.
Yeah, it was like, it's really interesting. In 2015, there was a paper on how does turbulence within clouds affect precipitation? And you want to include that on a global scale. Over hundreds of years, centuries, right? How's it? Yep. And another thing was, let's see, different architectures. So I don't know whether, I'm not convinced whether this will actually work or not. They're still trying to sell their their product, but there's this huge chip. You may have heard of it, Cerebrus, but it has 800 on one chip, 850,000 cores on a single chip. It's like this big.
How much memory does it have?
How much memory?
40 gigs.
So, no, so it's 40 gigs of SRAM, which is very fast, and that's, yeah.
It's 40 gigs of SRAM, and it's in a lot of our simulations, the ultimate limiter is the bandwidth from the CPU to the RAM. This would skip that step. So if you could fit the like densest part of your simulation, the part of your simulation that's using all of the compute in 40 gigs, it would be orders of magnitude speed up. Yep. So, you know, these things at only like 100 grand, like we can pull together that much, right?
100 grand.
Yeah.
GoFundMe page. You only need one.
Yeah. But I think that's it. Like this was discussed, you know, after we broke. So.
After you went broke.
No. I have no idea. I know of somebody, my former advisor, Tom Abel, he has access to one of these. It's the benefit of being in Silicon Valley. I think he could compile Enzo on it. So that was one big thing. Yep. Yeah.
Those on these hopeful notes, comments, questions.
Any comments?
Well, kinda. So it's my point was really that like the likes of an illustrious run will soon become impossible because we'll try to do bigger and bigger illustrious style runs, and it will just become very difficult to be managed by a small number of people. So we really need to think a little bit bigger and get the whole community involved in very, very large runs. Like this is obviously this would be another level above that.
Yeah, I was thinking like a decade in the future.
Yeah, at least I would.
Yep.
Yeah. If you wanted to speed up simulations by the order of magnitude, you would need to switch to a different limiter, and something like this would be that kind of shift.
Yeah, I think that's one thing I was thinking of. It's like, you know, pulling together our own efforts.
Yeah, exactly.
And I don't think it's one run. I see it as a suite of runs.
Yeah. And I think everybody gets involved and everybody gets access to the data.
Yep.
And then everybody kind of, you will need some buy-in. There's no doubt about it. Sorry, Mark.
I was looking up.
Just throw it.
Yeah, kind of done now. But like, yeah, no. So just to reiterate it again, I guess, like, you know, everybody gets access to the data, but like, and it's probably good for early career researchers to be able to get involved at the start. You know, you have the difficulty to balance out everybody wanted to put their own flavor into the simulations versus trying to get them actually off the ground. But I think that would be doable, I think.
Mm-hmm.
You need some infrastructure to manage it, but I think ultimately it would be good. Obviously, you're right in the sense of like, you might hurt creativity a small bit because then you're only running one simulation, but it could be balanced out by, you know, obviously smaller scale simulations as well.
Right.
But very large simulations and then different institutes running very large simulations is impractical in the long run.
I think so, yeah.
You know, it's just not possible.
Mm-hmm. It's also like a waste of power as well. You know, taking 3 months to run.
Duplication can be good.
Right.
Or it should be, you know, organized duplication. So decide more, you know,
Yeah.
Agora type of experiment.
Mm-hmm.
Maybe a quick comment on this. So I guess we are never going to like fully solve the problem. There will be always like finer details. So as we approach a more and more accurate solution at any level, I think we will want to understand what's the uncertainty at this point in for understanding of like galaxies, black holes,
right?
Which going back to John's point of a suite of runs. So how do we characterize our level of uncertainty at any point?
I see this as a suite of runs.
Yeah.
Varying some of the critical parameters, or maybe that could be a few different codes where people try and do their best, and maybe having that subset of outputs characterizing sort of the best knowledge of the community. That I think it has a lot of value. And so, yeah, I don't know. Yeah, I'm not sure what's the right level of either duplication or like different groups pushing in different directions, but I think it's very important to characterize the level of uncertainty.
Yeah, because it's, it's completely nonlinear and complex how the different types of subgrid models play together with the numerics of it. And
yeah, and I guess for machine learning, for example, any
it's right here, quantifying uncertainty. So
yes, right. So if we are to trust any machine learning model to do actual inference of the like real universe, we want to make sure that the model is robust to all of those uncertainties. Yeah. So yeah, it is very important to train on like a variety of models.
Okay, I think it's past 5 p.m. So if I understand correctly, we should wrap up here. But thank you very much all. It was really a lot of fun to listening to all the discussions and the comments.